We're going to talk about rolling motion. Starts on page 78. Stop the live stream buffer. Okay, got it. And now I'm going to remind you of this device right here. Hopefully the markers haven't dried out since last time we did it. This is pure rotation, right? You can see this thing, it's rotating. And then there's translating, which is this, right? Moving from point A to point B, or you could say the center of mass moves from one spot to another. Pure rotation is the object is spinning about its center of mass or some other pivot point. I guess you could say this is rotation too, right? Swinging motion. But now I want to point out the bizarre nature, complicated nature of rolling motion. So we're going to start right here. Well, let's start with this red marker on the ground here. I'm just going to try and push this. Best I can. And you can see that the points on the object do not all take the same motion. In particular, the red line here is a point on the edge. The black line is the center of mass. Now we're going to restrict ourselves to simple objects like spheres and cylinders because I don't want to talk about non-round rollers, but if you want, at the end of class, I've got some hidden over there. There's weird objects that have some of the same properties here. Like we could show triangular wheels or things. And anyway, we talked about this last time. I want to emphasize this point right here. So just before this point hits the ground, I'll call it just before impact, right? The velocity is basically straight down. Just after, the velocity is straight up. What does that say about the velocity at the very instant that it makes contact? 0. Okay, so I'm going to say point of contact with road does not move relative to road if, there's a giant if statement here, if we do rolling without slipping. Now, to be fair, that's the only thing that I'm going to put on the test. So I might mention rolling with slipping, talk to you a little bit about it, but I want to be clear, we're going to make this assumption on test day, okay? So, but generally students are curious, and so maybe I'll show you one more thing. Maybe you've done this experiment before on a bowling alley or with a ball. So if you could give me your attention for a second here. If I hit this ball just right, you can see, watch the motion of it. Watch the motion. Did you see how it slips for a while? You can hear it. Listen. When the sound stops, it's no longer slipping. That sound is coming from the slipping. And if you can see this up here, you see all these dots. So in this case, you can literally see the motion change. Notice it, instead of spinning rapidly, it makes this nice steady pattern. This right here is rolling without slipping. This is rolling without. If I do something weird where it does that, that's rolling with slipping right off the table. All right. All right. Now, to be fair, we are not going to deal with that slipping. There is a homework problem I'll show you later. If you are curious, you can learn more. Now, if we have I better check. Okay, whoops, I'm not on the right camera. Give it a second. If we are rolling without slipping, the following things are true. The acceleration of the center of mass, that's this black line here, the center of mass, is equal to r alpha, where r is the radius of the rolling object. The velocity of the center of mass, what do you think that's going to equal?
R omega.
R omega. So as long as it's without slipping, these old rules still apply. What about the distance of a point on the rim? Or in this case, the distance traveled by the center of mass is going to be related to the angle. And sometimes we might use r delta theta, so maybe I'll put in delta theta, right? Usually we say theta initial is 0, but just in case. Now, what's weird about this motion can be modeled. Remember, there's pure rotation and there's pure translation. But when this object is doing this, it's both, right? Let's see if I can start it in the right spot. Notice it's rotating about the center of mass, but the center of mass is also translating, right? So in this case, we got rotation and translation. Whoops. About the center of mass. So if we do an energy equation, there's going to be a 1/2 I omega squared plus a 1/2 mv squared. And it turns out maybe I could mention this really quick. See this point in red here? Velocity down, velocity up. What happens is, as this thing is moving forwards, it's rotating backwards, right? Think about it. Watch the red marker here. In particular, right now, notice the marker is rotating backwards while it's translating forwards. It's the combination of this translation of the entire object and the rotation this way, which causes this speed to cancel out at the very bottom at the instant it touches the road, right? It's rotating backwards and moving forwards, right? And so the idea is that's why the velocity can be 0 at the point where it touches the road. If you care, what do you think is true at the top? Look at the top of it. Which way is it rotating at the top? With the motion or against the motion? Yeah, so take a guess what happens to the velocity of the top of the wheel. It's twice. It's doubled. So it's this weird situation where if it's without slipping and rolling, the top of the wheel goes twice as fast, the bottom of the wheel doesn't move, and the middle goes the average speed. Cool, right? If you really want to understand this, you have to take an advanced course, right? A dynamics course. But we're going to try and do some simple versions with energy. Okay, I want to say one more thing here. Actually, I want to say a lot more things. In this case, This is such an important fact. You just have to know the point of contact is not moving. This is crucial. If you don't have friction, something's not going to roll, right? You need friction to twist the wheel backwards. However, the point of contact is not moving. So even though there's a frictional force, it does no work. Think about that. The friction is not doing work because it's not displacing the wheel. It's just, but if it wasn't there, this thing wouldn't roll, it would slide, right? If there was no friction and you push something, it would just slide like this. So you need friction to make it start twisting. Oops. You need the friction to make it roll, but the friction doesn't do any work. Weird, right? Now the friction does exert a torque, and we could talk about that, but all right, and we will. What else do I want to say? All right. I guess I'll say it now. There's a weird phenomenon that oftentimes makes these problems a lot easier. We could choose the center of mass as the pivot point, and that is the default. However, there's a special mathematical trick that works for this problem only that can actually simplify some problems. It's a trick called the instantaneous pivot. Now, what I mean by this is at any one instant, some spot is touching the bottom. Agreed? No matter where this thing is, at some spot, right now it's this spot, right now it's this spot. At any one time, you could imagine this thing as being pivoted about that spot, the point of contact. Now, to be clear, the point of contact would change a second later. So each instant, you could imagine a new pivot point. But the idea is you can actually visualize rolling without slipping as swinging about the bottom. I swing about the bottom. I swing about the new bottom. I swing about the new bottom, etc. forever. Now think about this. If you do this as swinging motion about the bottom, it's exactly like the pendulum problem that we already did in lab. Remember that? We did an energy problem for swinging about the bottom, or torque. So what's really cool about this is you can either do translation and rotation about the center, or pure swinging motion about the bottom, the instantaneous pivot. Mathematically, they give the same results. Did that make any sense? There's something weird about it, though. This one, right, if I do rotational energy about the center of mass, I would need to use the moment of inertia about the center of mass. If I do this weird way where it's pure swinging motion, the moment of inertia would have to be about this point, and I'd have to use the parallel axis theorem. So if you want to use the instantaneous pivot, you got to remember to also use the parallel axis theorem. Now, we've got to do some math. I'm going to show you the math, but first I'm going to ask you a fun question. Let me see if I can get it over here. Come on. And then I guess you two are right in the frame if you care. So if you want to just stand up out of the way for a sec, that'd be cool. Yeah, thank you. Okay, cool. Thanks. Okay, we're looking right here. The idea is we can have objects and we could roll them down this hill. Right? We could do different objects. Like, for example, I could do a disc or a ring. And if I start them at the same time, let's just do this one. Which one do you think would finish first? What factors do you think would affect it? Okay, so you think the mass would affect it, right? How much that seems like possibly a reasonable assumption, right? What about the size of it? What if I did two different shapes like this versus these, right? Will the radius affect it, do you think? Yes. What about the mass distribution, the shape? Right? These have the same radius, and it turns out they're close to the same mass. So if they have the same mass and same radius, do you think they would finish at the same rate or not? No. It's not obvious, is it? So why don't we do the math, then run the race? You know what I'm saying? Okay, let's do some problems and we'll come back. Oh, that's where that happened. That's cool. Look at 10.49. Is that what I said? Yeah, oh, 59, 10.59. I'm sorry, page 79. Basically want to be an expert at this problem and the next problem, okay? 10.59 and 10.60. We're going to assume rolling, was it with or without slipping? What's going to be on your test? Without. We've got an incline, there's some angle theta, and there's an object up here. Now we could start with any object you want. Oh, and then we kind of discussed this. We were wondering if mass, radius, the shape, it might affect things. So you've all made your decision. It's okay if you're wrong, we're going to learn. And let's do a conservation of energy problem. So let's assume object has moment of inertia about center of mass, just to be clear, right? Because there's that instantaneous pivot. You always got to be clear whether you're talking about instantaneous pivot or center of mass. About the center of mass, I. If it helps, I'm going to point out a disk is 1/2 mr squared. That's a disk. And these are all about the center. Oops. A spherical shell is 2/3. Solid sphere is 2/5. And oops. Just mr squared is a thin ring. I'll mention something about that really quick. If you're curious, how thin does it have to be thin? Talk to me later. Okay, I promise I will explain it. But for now, let's just assume as long as the radius is much, much smaller, and how smaller? Probably 5%, 2%, something like that. As long as this thickness is about 2 to 5% of this entire thing, it's pretty much a thin ring. Okay. And in general, notice most of these take the form of k mr squared in general. You notice that where k is some constant? So in a lot of classes, what they're going to do is they're just going to say, assume the moment of inertia is k mr squared, okay, where k is some. That way, we're kind of doing the derivation in general. Then you can look up the factor. It's 1/2 or this 2/3. Has anybody ever heard of something called the radius of gyration? Okay, we'll talk about that some other time. All right. I'm going to write down the energy problem. K initial plus U initial everybody's cool that I'm not wasting time with the spring. I'm hoping. Let's assume we release from rest. And let's draw our final picture here. Do you agree in the final picture, it's going to be moving with some speed v, and it's going to be rotating, let's see, rolling this way with some omega. That's kind of sloppy, but. Can you see that a little better? All right. Now I want to make sure you're all ready to go. I want to start at the same time. So I don't usually do this, but let's make sure we're all good. Is everybody cool? Okay, there's some tricks in here. You got to know these tricks. Okay, so first off, we usually attack the work. What's the work done by friction in this case? 0. Do you remember why? Point of contact with road has 0 displacement relative to road. You were right. That was that garbage I was talking about, the instantaneous. Is that good enough? Everybody cool with that? Obviously, if there was no friction, there would not roll at all, but that friction doesn't do any work. To me, that was extremely confusing when I was a student. I hope that's good enough. I'm not going to say it again and again. What about the work done by the normal force? Perpendicular. It's perpendicular to the displacement. What about the work done by gravity? Is gravity going to do work on this? Yes. Yes. Do I need to worry about the work done by gravity? Or are we going to account for it in the U? We're going to account for the gravity in the U, right? So we're not going to include it in this term. So then, is everyone okay that the work done is 0? So now, what types of kinetic energy do I have? Oh, initially, what else is 0 here? Kinetic energy. Yeah, why is it 0 initial? If we release it from rest, that helps us get rid of this term. And then what's a good thing to do for the gravitational potential energy that we usually do in every problem? Yeah, and now because we know better, I'm going to do it this way. We're going to go to the center of mass in both states. But notice, it's going to be exactly the same if we go top to top, bottom to bottom, or center to center for a straight line. For swinging motion, that's absolutely not true. Remember that? If something's swinging, that's not true. So this is going to be height initial, and we're probably going to call the lowest point height final equals 0, or maybe I'll call this like that. However you want to do this. Does anybody remember how h relates to the distance traveled? For example, in this case, what's a good name for the distance we travel down the ramp? Pick a letter. D. I like D. Okay. Do you agree that this angle up here is theta? So what's a good name for this height? H sine theta. Oh, wait, not H equals, not H sine theta, but yeah, you got it. I knew what you meant. Is everybody okay with that? So now, what would be, how would I write the initial potential energy term? equations. Gravitational potential energy, what's the general equation? mgh, mg, and what's our particular height in this problem? D sine theta. That's the left side. Is anything going to equal 0 on the right side? H final, excellent. So that's going to set U final to 0. Just making sure I'm going kind of quickly. So the next part is the really important step. This is what's different. What is the final kinetic energy? What equation should I write down for kinetic energy here?
1/2 I omega squared plus 1/2 mv.
Exactly, because it's got both terms. So we don't write 1/2 mv squared. We don't write 1/2 I omega squared. We write both. Because it's root, and that's the main difference here. And to be clear, when you do this type of problem this way, we're using the center of mass moment of inertia because we're not using the instantaneous pivot. If we use the instantaneous pivot, it's a trickier problem. It should work out the same, but then it would be pure swinging motion and you'd have to use the parallel axis there. Now in lab on Thursday, do you remember I told you something? When we're doing these problems in chapter 10, usually it's best to do everything in terms of rotational variables, right? Like the swinging motion, we solve for omega final and then we multiply by r to get v final. Or we solve for alpha in the torque problem, and then we multiply by r to get acceleration. Do you remember that? Well, here I have both. The trick at this point is we can relate omega and v. What is the relationship if rolling without slipping? If rolling without slipping, how are omega and v related?
V equals R omega.
V equals r omega. All right. And to be clear, in this case, I mean the v of the center of mass equals radius, and that's because of the weird motion that we talked about earlier. That's it. That's the main difference. At this point, you're going to plug in and solve for some letter in generally every physics problem. So now, let's think about the question we want to answer. We want to figure out which of these objects gets to the bottom the fastest. What could we solve for in this problem that would help us identify which one gets down the hill the fastest? Velocity, or v, speed in this case, but yeah. If we solve for the RPMs, that doesn't necessarily tell us which one gets down the hill the fastest. If we solve for v, that says which one got from A to B fastest, or from initial. So let's, in this case, eliminate omega. So when I solve this for omega, what do you get? V over R, okay? Let's plug that in. And I don't know if you could see this, because these i's are going to have r squareds in them. Is the radius going to matter? Look. When I plug, oh, let's just do it. Okay, let's do it. Yeah, the radius doesn't matter at all. What else doesn't matter at all? We'll find out.
The mass.
The mass! The only thing that matters is the shape, which gives us the constant. Isn't that crazy? Okay, that's my claim. let's finish this. 1/2 I times V over R. Now, in this case, I guess it doesn't matter if you use capital R or lowercase r. You do want to be consistent. Here I used uppercase, here I used lowercase. I'm a bad person, sorry. But notice what you get right here. They generally look like this. A 1/2 factors out, and I get an I over R squared, the rotational equivalent of mass in units of kilograms, right? This has kilograms, meters squared, divided by meters squared. I think you get that, right? The 1/2 factors out. There's an I over R squared. There's a V squared. Take a second to make sure you agree with that. And then out of all this, maybe I'll solve for V right here. Gonna get some big square root of when I divide this, the 2 is going to come into the numerator. Right, 1 over 1/2, and then I get like that. If you want, I'm going to plug in the general formula, but I got to make some space on a board somewhere here. Oh, geez. What I'll do is go way over here. Okay, so I'm just going to rewrite that result over here and finish it out. Did I screw up the math, or was that right? Good. And now I want to remind you, remember the general form right there? The general form of the moment of inertia was, let me get out of the way. Some factor which, isn't this insane? What drops out in this term? The R squareds. What does every term have in it? So the mass and the radius don't matter at all. Isn't that trippy? So now we got 2g sine theta all over a constant plus 1. K is either 2/3, 1/2. Just to remind you, K is equal to 1/2 for a disk, 2/3 for a spherical shell, 2/5 for a solid sphere, and 1 for a thin ring. So those are just the various constants that K could be for typical rolling objects. So which one's going to win the race? If we do a thin ring versus a disk. That's sloppy. Let me do like that.
The thin ring.
Why does the thin ring win? Explain.
Because you got 1 + 1, 2, you can solve it 2 on the tops. It's just GD.
Yeah, but so what happens to the denominator? Which denominator would be bigger? Thin ring or disk?
the thin ring.
So if you have a big denominator, what happens to your V? So which one wins? You want, if you want to get down quickly, do you want to have a big denominator or a small denominator? Which one gives you a smaller denominator? 1 + 1 or 1 + ½ Which is the smaller denominator? That wins. See it? Yeah, yeah. So let's check it out. Okay, so I'm going to be doing the demo again, just so you know. You guys are probably going to want to stand up a little bit. Isn't that crazy? Okay, and then it's pretty sloppy back there. Let me grab a green screen. You help me catch these objects at the end. Yeah. Black one. Yeah. So I might need you to help me hold this too. Does that look okay on Zoom? I don't know. Is anybody on Zoom? Are you actually there? Can you see that okay? Looks pretty good to me, but. All right, whatever. It takes some time to respond, right? So what was the ring? Oh, here it is. Which one should win? Which one has mass close to the axis? So this one's going to be easier to rotate, less energy gets wasted on the rotational kinetic energy. Does that make sense? If the mass is close to the center, it's easier to get twisting, it's easier to get it rolling. 1, 2, oops, I'm going to hit that basketball. Okay, cool. Go ahead and set them on the side. Now I have 2 cylinders. And I'm going to start them with their center masses using this. I'm going to make sure both center masses start at the starting line. I'm not perfect, okay? But which one of these should win the race? The big cylinder or the small cylinder? Same. Radius and mass doesn't matter. 1, 2, 3. Pretty close to the same. Do you agree? We could try this again. Two spheres. These are both solid, I believe. Okay. Which one of these spheres should win the race? Tie, yeah. Now, what's weird about these is cylinders don't tend to, they're going to go straight down. So if this isn't perfectly level, can you help me maybe scoot these things back a little bit? So they might roll off the track, but just keep an eye on them. Ah! The tape must be. All right, all right. That was pretty funny, huh? Real life is not always convenient. Okay, so let's try this again. Pretty close to the same again. Do you agree? Who should win between this basketball? Can you hand me a pool ball? Who should win between these two? Basketball or whatever, solid sphere? Basketball has most of the mass close to or far from the axis? Far, right? It's the shell. So the solid is more concentrated. Which one should always be the fastest? solid sphere. So hopefully, I need to move that crap out of the way. It shows up all over that. Here we go. 1, 2, 3, go. You see that the pool ball does finish the race faster. All right, is that enough of that? Let's give him a round of applause here. Thank you. All right, so I'm not trying to lie to you. Hopefully that demonstration made it. Isn't that strange? Rolling motion is weird and special. Come on. There we go. So in general, this is the technique for using energy. How did you feel about using energy on rolling motion? Okay. I want to show you how to do a torque problem. So the idea is, on your test day, we've done a swinging pendulum, we've done the pulley with 2 masses, and now we've done rolling motion. You're probably going to get 2 out of the 3, and I don't know which 2. So you got to know how to do roll. These 3 problems you need to be excellent at. The ones we did in lab and the ones we're doing right now. And I'm not sure if you're going to have to do torque or energy. You can do torque or energy on all of them, right? For the pulley system, right? We did it using torque, but homework problem 10.53 does it with energy, right? So you could, all right, I'll talk more about that in a minute. Let's do the torque problem for this, okay? So I need to erase something. I'm going to erase this board. Give me a second on Zoom.
There's a case where we have to calculate B using voltage quantities.
What's that? Calculate what?
Or like change B.
Yeah. So basically, in these problems, let me see which board I'm on. You know how a physics class is. This part is pretty much the same for every problem, and then I just say, give me this letter, will you? I can make you solve for theta, for D, for not for M because it drops out. Not for R because it drops out. Got it?
Yeah.
Yeah, I could make you solve. Now, here's the thing. If I did give you the mass and the radius, I could make you solve for the moment of inertia, right? So I could include M and R and ask you to solve for I. Got it? It's just basically alphabet soup. You solve for some letter.
But
This is the physics, the rest is math. Yeah, go ahead.
B isn't equal to change in data.
Yeah. Oh, okay. This is interesting. So remember, D is the distance traveled. So if I write it like this, right, this theta would be the angle of the ramp. So D is not equal to R theta in this case. It would equal, like maybe for this case, you could, right? Like you can't have more than one thing called the same letter. You could call it delta phi for the angle that this thing rotates, where this is the revolutions basically, except we're going to use radians. You know what I mean?
Yeah.
So I could ask you, how many revolutions does the ball make as it travels downwards? You solve for D, divide by the radius, convert to revolutions. Did that make sense? Yeah. Or I could say, give me the rotational rate in RPMs at the bottom. You solve for omega instead, convert to radians per, or convert from radians per second to revolutions per minute. Good?
Yeah.
So if you do a couple of these, you'll be automatic. Okay. All right. Good question. Excellent question. All right. By the way, all of this is written up in horribly gory detail in the solutions, including all 3 methods: torques, energy. So if you need to, you can use the solutions later. It's a little messy. Clean this up. So let me do this. Here's the center of mass. What is one force that acts on the object as it rolls down the hill? This is the object that's going to roll down. What's one force that acts on it?
Gravity.
Gravity. Where does that act?
The center of mass.
At the center. Is that going to cause a torque about the center? I need a bigger picture, but I'm going to wing it. Can you read that at all, or is that too small? Good enough? Okay. What's another force? It's sitting on a ramp. Normal force. Which way does that act? Show me with your finger. Yeah, angled, right? It's not straight up. It's perpendicular. Is that going to cause a torque? This is the line of action. For the normal force vector. Notice it goes through the pivot. It causes no torque. Are there any other forces on this thing as it rolls down the hill? Friction. Which way?
The right.
Okay. Does that make sense with the rotation direction? What direction is this thing going to rotate? Show me with your fingers. That way. Do you agree? My thumb, right? Is this friction going to cause this to twist the right way? Yeah, right? If there's friction here, it's going to push back and make this rotate the correct direction that we expected. There's friction here, it's going to push it this way. That's good. Is the friction going to cause a torque? You bet your ass. It's the only force that causes a torque here. So now, the sum of torques equals I alpha. The only thing causing a force, or the only thing causing a torque is going to be, actually, I'm going to add this in here. You need a line of action for mg. And m, both of those have a line of action through the pivot. Do you agree? What is the torque due to friction? I'm going to call this direction positive. Right? If there's only one force and it's going to cause rotation this way, I'm going to call this way the positive direction. What's the equation for torque? Do you remember? Any equation? RF sine of some angle. So in this case, that's going to be, what's the distance? What's a good name for the distance from the center to the edge? Radius. In this case, the force is friction. And then I need the sine of some angle. What's the angle between this vector and that vector? 90. What's sine of 90? 1. So we see RF equals I alpha. Well, at this point, couldn't I just plug in F equals mu static times the normal force? Or is it mu kinetic? Which is it? Why do you say mu static? It's rolling without slipping, so this point of contact is not moving. But it's not mu static n. Why not?
on the verge of flipping.
We don't know if it's on the verge of slipping, right? Crap. So I don't know a value for F. Shoot. Is there anything we could do? We've done sum of torques equals I alpha, but we need more information. Can you think of any other physics laws in the frickin' universe? What's the one law you know from physics class forever? Boom. Can't we do this as well? Well, I'm going to draw this a little bit better so you can see it. There's mg. There's the normal force. That's the frictional force. And you agree it's accelerating this way? So let's call that the positive direction. Down the hill is positive. In this case, what is one force in the horizontal direction or in the direction of the acceleration? Give me one force in the direction of A. mg sine. What's one force that's opposite the acceleration? Are there any others left and right here, or in the x direct or parallel to the plane? Any other forces parallel to the plane? No. All this equals? Okay. At this point, could we solve this equation for F? Minus MA. Now, we're very close to being able to plug this in, but this one has an alpha and this one has an A. Does anyone remember how A and alpha are related if rolling without slipping? R alpha. At this point, you could plug this in to here and solve for alpha. Agreed? So instead of getting the speed at the bottom, we could get the angular acceleration. Does everybody follow that? You could plug this into here and solve for something. What if I wanted to get the acceleration? By that, I mean the translational acceleration. What would you do if I said, get me translational acceleration? Exactly. Solve for alpha, just like always, then multiply by r. Or check this out. You could also take this velocity and plug it into kinematics and get A. Right? Or, woo! You could actually solve for this alpha, multiply by R to get A, and then do kinematics to get V. Am I losing you? Or is this, I'm trying to show you that this problem has a lot of ways you can solve it, and they're all consistent. You can use kinematics, torques, and energy for rolling without slipping down a ramp. Cool? All right. Now, finally, I promised I'm going to deliver. Instantaneous. Thank you. Give me a sec, I'll get out of the way. What is one force? Well, we know the forces. They're exactly the same, right? I want to just make sure I'm on the right whiteboard. I'm freaking out right now. Okay, we're good. Let me get in here and draw the same exact forces. It helps if you draw these pictures really big, doesn't it? You got to get in that habit of drawing bigger pictures, even if it wastes some paper. Where is the instantaneous pivot again? What does the instantaneous pivot mean? The bottom. Which forces cause no torque? Which forces cause zero torque about the instantaneous pivot?
Normal.
These two lines of action through the pivot. So about instantaneous pivot, N and F cause zero torque. I hope you see why this is a cool trick. Friction is the force we know nothing about, and this torque equation eliminates it. I prefer this method. It turns out it only works for rolling without slipping, but it's easier if you have that case. But you've got to help me out here. If this angle is theta, what do you think that angle is? Right there where I'm pointing. What is that angle?
90 minutes theta.
Theta. You could tell this is a skinny angle, that's a skinny angle. But it's exactly the same as this one here, right? You agree? So if you take the time and draw it out, how about I do that, right? If this is theta, this is 90 minus. If this is 90 minus, this is 90 minus. If this is 90 minus, this is theta. But again, this drawing it skinny helps. That's a theta in there. Sorry if you can't see it over there, far forward, people. So now let's just do this. The torque caused by mg should equal I alpha. And now we need to be careful. This moment of inertia is not the same as this moment of inertia. I'm going to say that again. Please look at the board. I know you're busy, but this I is not the same as that I because the pivot point has changed. So I'm going to label this one as center of mass, center of mass, center of mass, center of mass. This is about the instantaneous pivot. Do you see the subtle difference now? Mm-hmm. If we don't account for that, the two equations don't match up. Well, I know I instantaneous pivot is going to equal I center mass. What was the parallel axis theorem? Plus what? MD squared. What is D in that parallel axis theorem? And I need to zoom out just a little bit.
The distance between the center of mass and the line of action.
The distance between the center of mass and the other axis, right? This is a parallel axis theorem. Here's one axis. Here's the other axis. What's the distance between them for this particular problem? Radius. So in this problem, D equals radius. What does the torque do to mg? It's the force and the distance. Well, what's the distance from the pivot for mg? What's the distance from the pivot to the point where mg is applied? What's this distance?
Radius.
Radius. What's the force magnitude? Is there an angle between? Is there an angle between the r vector and the applied force? What is that angle in this case? So this one actually is theta instead of 90. Equals the moment of inertia is and while it may not seem obvious right away, I'm going to show you something. See how this has an I plus mr squared in it? Look at the other one. When you plug this friction into here, you're going to get an R times mr alpha. You're going to get the same result. Do you see it? mr squared alpha will happen when you multiply by R. And so when you plug all that junk in, you get the same answer. Isn't that wild? All right. And then give me just a second. Now, I did this one with you all the way. You guys need to be able to do one yourself without me, and that's what the next problem is all about. Let me point that out. Look at 10.60. That's this right here. Look at this thing. You got a yo-yo, right? Now, I'm going to just write, when you unravel this yo-yo, watch it carefully. Which way is it going to move if I hold the string like this? Is it going to go straight down, or is it going to go down and to the left, or is it going to go down in this way or down in that way? I don't want to think about it. Think about the forces acting on it. Which way does mg act? Which way is the string acting? Is there anything left or right? Right? Isn't that interesting? Maybe you've thought of that before, maybe you haven't. Now, why am I bringing up a yo-yo right now? I want you to think about this. The yo-yo is rolling down the string without slipping. It's like a ball rolling down a hill, only the ball is rolling down the string. So if you're doing a yo-yo problem, right? This could be the instantaneous pivot, or this could be the center of mass. It's exactly the same math. You could have this thing, you could do an energy problem as it falls, you could do torques about the center of mass, or you could do torques about the instantaneous pivot. So as a way to see if you really understand this, go do the solutions. Use the solutions as much as you can, do all these methods. Then try the yo-yo method, or the yo-yo problem with all three methods. Got it? And then you'll probably be ready for the test, if this shows up on your test. And since you got another test and a final, the odds are good it's going to be somewhere on one of your tests, right? All of these problems that we covered, which was swinging motion, or pulleys with translating masses, or rolling motion. All of these will show up at some point in your test 3 or your final, almost certain. Got it? Not all on one test, but probably there. So you got to know these problems. Should we take a break now? Or any questions about this? Oh, wait, I've got one. I've got 2 identical yo-yos here in terms of mass, one exception. One has a skinny axle and one has a thick axle. The axle has negligible mass, it turns out. So it turns out the mass of these are very close. In particular, they're only 1/10 of a gram different, it turns out. Angus drilled out the center of this axle. So basically, these are identical in every respect except for the spindle. Which one do you think is going to get down the hill faster? If I let go of these 2 yo-yos, which one do you think is going to get to the bottom of the string faster? Just take a guess for fun. Tie? I hear a tie. I hear larger radius. Anybody want to go skinnier radius? Okay. Whoa. Clearly the one with the larger radius. So what was your reasoning?
this gives a faster output?
Turns out it's complicated. So I would say this. With these types of problems, I always just work it out on a piece of paper because it's not always obvious. And I may or may not have been writing a test question for you and discovered this weird case where I'm not going to say much more. So basically, you should know how to do the paperwork, okay? The paperwork guides your answer. Understood? Now take your break. It's weird. Yeah. I'm going to stop the live stream and I got to remember to restart it when we come back.